When you really stop and think about it, our planet probably shouldn't even exist. It started its life as a chaotic, fiery rock in what was a pretty violent cosmic neighborhood. So how did it become, well, this? A vibrant, living world, our only home. In this explainer, we're going to trace that incredible scientific story of Earth from a tiny speck of cosmic dust all the way to the world we know today. It's a story that spans billions of years, a story driven by cosmic violence, massive planetary collisions, and the slow, almost improbable emergence of the conditions that are just right for life. So let's start at the very beginning, not with the planets themselves, but with the very first ideas about how they even came to be. To really appreciate what we know now, we first have to look back at the intellectual journey that got us here. See, long before we had modern telescopes, the quest to understand our origins began with simple thought experiments from philosophers and mathematicians. The first major idea on the table was the Nebular Hypothesis. It suggested that planets simply condensed out of a rotating cloud of material that was hanging around the young sun. But in the 20th century, that idea got a major revision. Scientists realized it wasn't such a passive process. Instead, tiny particles inside a huge disk of gas and dust were constantly colliding and sticking together, growing bigger and bigger over time. You can almost think of it like a snowball rolling downhill, just getting larger as it goes. This absolutely crucial building block process is known as accretion. But to really get a handle on where planets come from, we have to zoom out. I mean, way out, to the origin of the universe itself. And this brings us to the most widely accepted scientific framework we have, the Big Bang Theory. The Big Bang Theory, which you'll also hear called the expanding universe hypothesis, is really the bedrock of modern cosmology. What it tells us is that our entire universe started from a single point of infinite density, a singularity. But here's the part that can bend your mind a little. It wasn't an explosion in space. It was an explosion of space itself. Just as Edwin Hubble observed way back in 1920, galaxies aren't just flying apart. The very fabric of space-time is stretching, and it's carrying them along for the ride. And through some incredible science, we've even been able to put a date on this huge event. The Big Bang is understood to have happened about 13.7 billion years ago. That number is a really critical anchor point for the entire cosmic timeline. So, what happened in those first few moments right after the Big Bang? Well, an unimaginably rapid expansion. In just 3 minutes, less time than it takes to make a cup of tea, the universe's basic energy started converting into matter, forming the very first atoms. But for the next 300,000 years, it was still just a foggy, opaque plasma. It wasn't until it finally cooled down enough that light could travel freely, making the cosmos transparent for the very first time. Now, it's worth noting that the Big Bang wasn't always the only idea out there. For a while, the steady-state theory offered a different vision, one of a universe that was eternal and basically unchanging. But as more and more evidence for an expanding, evolving cosmos piled up, the scientific community moved pretty decisively in favor of the Big Bang model. Okay, so the universe is expanding. It's cooling down. And within this expanding cosmos, gravity started to do its thing, pulling all that newly formed matter together into these vast clumps. This is what set the stage for the next level of creation, the formation of galaxies, stars, and eventually, our very own solar system. And to even talk about galaxies, we have to get our heads around the immense scale. We measure these cosmic distances in light years. It's so important to remember this is a measure of distance, not time. It's the incredible distance that a beam of light can travel in one single year. Understanding this really helps us grasp the sheer size of the things we're about to discuss. All right, so building a planet happens in stages. First, gravity pulls gas and dust in a giant cloud, which we call a nebula, into a spinning disk. Then, in the second stage, particles start sticking together through a process called cohesion, forming these small, rounded bodies called planetesimals. And finally, in the third stage, these planetesimals begin to collide and merge because of their gravitational pull. That's our key process of accretion again. And that's how you form the large bodies we call planets. Now let's zoom right in on our home. The birth of Earth was really just the beginning of the story. Its transformation from a molten rock into the complex world we live on today is a dramatic tale of intense heat, the separation of materials, and massive atmospheric change. Just try to imagine the newborn Earth, a hellish, molten, rocky world that was under constant bombardment. Its very first atmosphere was nothing more than a thin little veil of the lightest elements, hydrogen and helium, which was pretty quickly blasted away into space by the intense solar wind from our young sun. So, how did this chaotic ball of rock actually get its structure? The key process is a word you need to know: differentiation. As the planet heated up from all that gravitational pressure, its materials began to separate based on their density. You can almost think of it like a cosmic salad dressing. The heaviest elements, like iron and nickel, sank right to the center to form the core. At the same time, the lighter silicate materials floated to the top, and they eventually cooled to form the mantle and the crust. This incredible sorting process created the layered planet we live on today. The air we breathe today is the result of a three-stage evolution. First, that original primordial atmosphere got stripped away by solar winds. Second, a whole new atmosphere was formed from the inside out, as volcanoes released massive amounts of gas from the planet's interior. And finally, in the third and most transformative stage, life itself took over. Early organisms started performing photosynthesis, pulling in carbon dioxide and releasing the free oxygen that would change our planet forever. Let's just focus on that second stage for a moment. The process responsible for creating our second atmosphere is called degassing. This is just the outpouring of gases like water vapor, carbon dioxide, and nitrogen from the hot interior of the Earth. It's a process that actually continues to this day with every single volcanic eruption. Okay, so a layered planet with a stable atmosphere and liquid water on its surface, all of this set the stage for the final and maybe the most profound chapter in Earth's evolution, the beginning of life itself. So when did this all happen? Well, the fossil record, which is preserved in ancient rocks, gives us our best estimate. The current scientific consensus places the emergence of life on Earth at roughly 3.8 billion years ago. That's a really key date in our planet's history. The modern scientific view isn't about some single magical spark. It's about a gradual process. Life emerged from chemistry. Over millions and millions of years, in the planet's early oceans, simple inanimate matter began to assemble into complex organic molecules. And these molecules developed a remarkable new ability. They could make copies of themselves. This was the fundamental leap from non-living chemistry to living biology. So, there you have it, from the Big Bang all the way to the first living cell. That is the epic story of Earth's origin. Now let's distill this vast timeline into the key takeaways, the core concepts you'll absolutely need to have a command of. For the prelims, you really want to focus on the hard facts and definitions. You need to know the Big Bang Theory, the definition of a light year, and the meaning of key processes like differentiation and degassing. And of course, you've got to remember those critical numbers: 13.7 billion years for the age of the universe, and 3.8 billion years for the origin of life on Earth. Now, for the mains exam, your focus really needs to shift to the processes and the concepts behind them. You should be prepared to discuss how scientific theories evolved, to explain that step-by-step process of planet formation through accretion, to analyze how differentiation led to Earth's layered structure, and to detail those three critical stages of our atmosphere's evolution. Let's just quickly test that understanding with a sample question. Which of these processes is not related to modifying the atmosphere? Well, we know solar winds stripped the first one away. We know degassing created the second, and photosynthesis completely transformed it. That just leaves differentiation, which, as we talked about, is all about the planet's internal structure, its layers. So the correct answer here is B. And for a final thought, just consider this. How would you go about explaining differentiation, not just as a process, but as the foundational event that made everything else, from volcanoes to oceans and even life itself, possible? Understanding that crucial link between heat, density, and structure, that's really the key to understanding the very planet beneath our feet. A planet that was forged in fire and completely transformed by time.